Hi, so I'm Suzanne Schuett, and we're going to talk about water distribution and treatment. So you turn on the faucet in your kitchen and water comes out. The United States has over 1 million miles of pipes that deliver 34 billion gallons of water a day. Water is delivered through a vast array of infrastructure, including pipes, pumps, valving, and these are meters. These are more piping and valving. Storage tanks. We've all seen storage tanks, water towers around neighborhoods, clear well tanks. You have reservoirs. I believe this is Horsetooth Reservoir up in Fort Collins. Big reservoirs as well, produce hydroelectric power as well as drinking water. So water is pulled from rivers or reservoirs to a water treatment plant. This is the water treatment plant in Chicago. So once in the water treatment plant, the water goes through a series of steps or processes to become clean, drinkable water, or what is known as potable water. So as an overview, things come through a bar rack, they go into a mixing tank and get added with a coagulant. They then go through flocculation, sedimentation, filtration. They go to a clear well tank, they're disinfected, and then they're distributed. We're going to look at each one of those processes. So treatment begins with a bar rack, and this is what a typical bar rack looks like. It removes large items such as twigs and larger trash items like plastic bottles, anything that's in the water that shouldn't be. The bar rack is cleaned often so that water may flow through unfettered. In a large municipal water treatment plant, this is an automated process. So using a step or ladder moving screen dumps the debris and lets water flow through. Some bar racks have a mechanical arm which pushes the debris off to let the water pass through. From there, water travels through a finer opening screen. The screen catches leaves, wipes, bubble gum wrappers, anything that would be at the intake. This is one type of screen. This is an automated screen. As you can see, there isn't a big dumpster behind it, but there's a small refuse collection, and then the water goes through. So from there, this is our steps that talk about conventional water treatment. So we talked about bar racks and we talked about screens. The next thing that happens as the water goes through the water treatment plant is we measure the flow. How much water is coming in? The pH is tested and then it is adjusted. Drinking water pH is usually around 7. At this point, an acid or a base is added to correct the pH. The water is tested for a coliform. Coliform bacteria or organisms that are present in the environment and in the feces of all warm-blooded animals and humans. Not all coliform bacteria will cause illness. However, their presence in drinking water indicates that disease-causing organisms, or what's called pathogens, could be in the water system. Most pathogens that contaminate water supplies come from the feces of humans or animals. If there are high levels of coliform bacteria, sometimes an oxidant or disinfectant may be added at the beginning of the water treatment process. Although adding a disinfectant at the beginning of the water treatment process can cause harmful byproducts. Most water treatment plants disinfect at the end of the process. If you do have coliform in your water, a lot of times the health department will issue what is known as a boil order. And this is what a boil order would look like. So it's a public health advisory for E. coli, which stands for E. coliform. So why would you boil your water? Recent tests show that your water system is contaminated with an organism that can cause illness. So this is basically what a public advisor would say. You need to boil your water for the next 24 hours. In some of the mountain towns, a lot of times this happens during spring runoff when everybody who hasn't picked up after their dog, the snow melts and all of that is carried off into the water treatment system. If things heat up quickly, a lot of times the water treatment system can get overwhelmed and they can't disinfect as well as they would like. And therefore you have to issue a boil order. Sometimes after large rain events down here in Denver, we have something similar. At this point, a coagulant is added. Coagulation is the adding of a chemical, usually aluminum or an iron salt. And what it does is it destabilizes the fine solids that are suspended in the water. And it creates a charged particle that is attracted to other particles and makes them clump together. After the coagulant is added, rapid mixing takes place to assist the particles in meeting and therefore clumping together, or it is known as flocculation. Heavy clump particles are known as floc. These larger and heavy particles can now be removed by sedimentation or filtration. So a mixing tank is typically either round or square. So these are the mixing tanks back here, and then these are the flocculation tanks. Mixing tanks are based on detention time and velocity gradient. So detention time, or what is known as theta, is equal to the volume of the mixing tank over the flow rate into the tank, or what is known as Q. The velocity gradient, represented by G, is the velocity of two particles divided by the distance between them. Simplified, the velocity gradient is the rate of the particles colliding. Detention times in the mixing tanks are usually less than 2 minutes. So you have all this mixing going on and particles are clumping together and water's flowing from the mixing tank into a flocculation tank. The flocculation tanks are tapered and they use 3 separate compartments with different velocity gradients. This produces a dense floc that will eventually settle out. The flocculation tank typically uses a paddle wheel. Basically, it's a rotating arm with 3 paddles that go at different velocities. So the flocculation tank uses a paddle wheel to push the water to differ the collision rates. The outer paddle moves faster and dissipates more power than the inner paddle. Typical flocculation tank times are about 30 minutes. After about 30 minutes in the flocculation tank, next comes the settling tank, which is also called sedimentation. There are 2 types of settling. There are free, or also called discrete settling, and then there's flocculation settling. In free or discrete settling, the particles stay the same size, the same shape, the same density. Particles settle individually, and there's no interaction between the particles. In flocculant settling, as the particles settle, their size, their shape, their density, and their settling velocity changes over time. So this is a settling tank. So you have a mixing tank, you have a flocculation tank, and then you have a settling tank. This is also another view of a settling tank. In the settling tank, overflow rate, detention time, and weir loading rate are key parameters in designing a sedimentation or settling basin. A settling basin is where all the floc settles out. To determine the size of a settling basin, we use what is known as the overflow rate. Overflow rate is just another way of expressing settling velocity, or in other words, how quickly the floc settles out over time. The overflow rate equation is VO, or overflow rate is equal to the flow rate through the basin divided by the surface area of the basin. So overflow rates differ depending on the chemical used to create the floc. Detention time is the amount of time the water remains in the settling basin, which is the volume of the tank or the basin divided by the flow rate through the basin. The overflow rate equation is VO, or overflow, is equal to the flow rate over the area of the basin. As I said, overflow rates differ depending on the type of chemical used to create the floc. The detention time is the amount of time the water remains in the settling basin, which is the volume of the tank or the basin divided by the flow rate through the basin. A weir is almost like a dam with a small section cut out in the front. So this is an overflow weir. The cutout in the front causes a decrease in area for the water to flow through. It's a flow control type mechanism. The weir loading rate is the amount of water leaving the settling tank per linear foot or meter. Why is that important? Because if the weir loading rate exceeds the parameter, which is typically 10,000 or 20,000 gallons per day per foot, then solids may be carried off unexpectedly. Things are flowing out of the settling basin too quickly, and solids are going with the water. So this is a weir in a sedimentation or settling tank. A weir typically, like I said, is a notched small section cut in front of a dam. Typically, weirs that you see out in rivers over. So this would be your overflow. And then This is what people typically think of when they think of a weir. In water treatment, weirs look more like this. So the next step after sedimentation is filtration. So this is an example of open filtration system, and below that is a closed filtration system. Filtration is the separation of non-settable solids from water. The majority of water treatment facilities in the United States use sand and gravel. Water using gravity is pushed through the filtration media, and as water passes through the sand and gravel, fine solids are removed. As the filter media catches and sorts out the fine solids, it holds less and less water. Therefore, the pressure must keep increasing to push water through the sand. That increase in pressure is called head loss. When head loss reaches a significant level, the filter media must be backwashed to remove all the particles. So most water treatment plants have more than one filtration unit on it so that they can backwash one while they use the others. So we've been through the majority of the water treatment process. We've been through the borax, we've been through the screen, we've been through flow measurement and pH and adding a coagulant, mixing, flocculation, sedimentation, filtration. Next up is clear well storage. So a clear well is an enclosed tank used to store filtered water with sufficient capacity to prevent the need to vary the filtration rate with variations in demand. So during the summertime where people water their lawn, there's a high demand for water. Some days when it's raining a lot, there's a low demand for water. If you are constantly meeting demand and not having a surplus, then you are pumping more and pumping less and pumping more and pumping less. So the clear wells help soften that, right? You use your wells to provide during high demand. Clear wells are also used to provide chlorine or disinfectant contact time. Right? So disinfection is the process where a chemical is added to oxidize whatever residual organics are left and to kill pathogens. Again, disease-causing microorganisms. In the US, there are typically 3 methods of disinfecting water: chlorine, ozone, and UV or ultraviolet radiation. Chlorine is by far the most common method. It's effective, it's inexpensive. Chlorine can react with organic species in the water, and it can produce trihalomethanes and haloacetic acid, both of which are carcinogens, cancer-causing chemicals. Adding chlorine at the end, where there are minimized organic species, reduces the amount produced to safer levels. Ozone, another method of disinfecting, is what's called an allotropic, or a different form of oxygen. It's a powerful oxidant that reacts with organic materials. It's produced in a high-strength electric field from oxygen. And a major advantage of ozone is that the trihalomethanes are not produced. Regulation requires a residual chlorine. And so if you're using ozone, you actually have to add chlorine after the ozone so that you have a residual chlorine. Ultraviolet radiation is produced with mercury vapor arc lamps. So ultraviolet lamps are put into quartz sleeves and then placed into the water. You have the water inlet, the stainless steel chamber, electrical enclosure, right, and an outlet. And the water goes through, the UV radiates and kills all of the pathogens. So after clear wells and disinfections, the water is distributed by high service pumps to homes and taps where you can enjoy a clean, fresh, safe glass of water. That's water treatment. Thanks.